Hello and welcome everyone. I'm going to present adversarial multitask learning enhanced physics-informed neural networks for solving partial differential equations. My name is Pongpisit Thanasuthiwet. I'm from Osaka University. The outline is as follows, so let's start with the introduction. In the age of big data, deep learning and machine learning models have been heavily utilized a lot to solve various problems and shown very promising results as well. On the other hand, before the rise of huge black box models, scientists used to have their explicit description of how the physical models made prediction compared to deep learning. Both of them have their own weaknesses. For example, deep learning usually requires a lot of data to perform well, massive data samples, and neural net predictions are not really explainable. So neural nets can easily break physical rules. Physical modeling is very hard to obtain, especially a good, accurate one for noisy processes in which we do not completely understand. And it's not data-driven, so the data biases are not utilized by the model. To alleviate these problems, researchers have asked an interesting question. How could neural nets learn physics? And come up with a method which embeds physical rules into a neural network. The method is called physics-informed neural networks, PIN. PIN is primarily used for solving partial differential equations, which basically are languages for expressing physical systems. I will briefly explain about how pins work. First, we have a bold capital letter N for the nonlinear differential operator. We have U denotes the latent solution. And here we have lambda for PDE parameter. Pin will output estimated solution, and then we should prepare partial derivatives, which are elements of the nonlinear differential operator. Then we calculate f and put it as part of Pin's loss function. The other part of loss function is the MSE on boundary conditions and initial conditions. To summarize, the loss function consists of two components. First, the PDE constraint, and second, the MSE on boundary and initial conditions. To visualize what's going on here, I have put an elementary example of one-dimensional Laplace PDE. So the PDE is just setting the second order derivative equal to 0. So to construct the f function or to compute the nonlinear differential operator, we basically need two things: approximated solutions and second order derivatives, which are two main things that neural network will output. And I'm noting here that the second order derivatives can be easily calculated by using automatic differentiation with respect to x on u twice. Okay, and then let's construct the Pin's loss function. Here's the PDE constraint, the second order derivative, and here's the MSE on boundary and initial conditions. Unfortunately, no method is perfect. Pins have also drawbacks as well. And in this paper, we're trying to solve them. The problem number one is that pin is not generalized well for our distribution data points. And you can see that the predicted solutions and ground truth starting to diverging from each other on the areas where the network were not trained on. So our first proposal is to elevate this problem using multitask treatment to the PDE formulation to improve the generalization. The problem number two is that naive uniform sampling of data points could potentially degrade the generalized performance. As you can see from the right-hand side figure, that dynamically changing regions need more samples, need more attention here. So Our second proposal is to solve this problem by generating more training samples on the around the high loss regions where nonlinearity is high. And to metaphor this process, we kind of like having more adversarial samples. I will briefly explain about the preliminaries of this research. The first one is multitask learning, MTL, basically about learning shared representations between related tasks like task A, task B, and task C to enable the network to generalize better on each task. Here I put a very simple construction of multitask learning. So we kind of have two main focuses here. First is how can we deal with the multi-objective loss function, and here I put naive weighted average loss function. And the architecture is simple hard parameter sharing. Next is about adversarial training, mainly about training with adversarial samples together with the original samples to enhance the network robustness. Here I put the very famous computer vision based example so that you can see that we also have a kind of multi-objective loss function here, balancing the network attention between the loss from the original sample and the loss from the perturbed one. And here I posing an interesting question which later becomes one of the proposals of our method, is that what are adversarial examples in the context of solving a PDE? Well, let's talk about the proposed method. Here's how we could simply generate multiple related PDE for support learning to solve the target PDE. This is an example from Berger's equation. Let's consider this number. I call it lambda because it's one of the PDE parameters, which is called fluid viscosity. By varying lambda using this form of equation, we are able to generate multiple auxiliary tasks. And joint training them increases the generalizability of the software network because it's kind of like letting the network to consider multiple fluid dynamics with different viscosity. I'm noting here that I use Bayesian optimization to search for the base alpha star. For the multitask learning architecture, I use cross-stitch model, denoted by CS. Cross-stitch model utilize linear combination to weight between the effect of task 1 activation and task 2 activation. This process happens successively throughout the entire network until we get to the estimated solution for each equation. To calculate the multitask learning loss, as the first option we use uncertainty weighting, meaning that we use a kind of inverse of uncertainty to weight between PD losses, and then we also have the uncertainty penalty as well, encouraging training with more certain PD or more stable tasks. This is all under the assumption that the true solution distributes normally around the estimated solution with the uncertainty sigma. You might also wonder, how about using other multitask learning optimization techniques? As the second option, I use PC-grad algorithm. To briefly explain, PC-grad projects task I gradient onto the normal vector of task j gradient, and vice versa, to deconflict the gradient directions during training, and this make joint training multiple tasks more easier to update the network parameter theta, and that's great. As I mentioned earlier, we also introduce a way for the network to fight nonlinearity, which potentially causes high loss regions. The idea here is that we actively sample more difficult to predict data points by a neural network generator, which trying to first maximize the neural network solver loss or the multitask learning loss that I've just introduced. We call this part adversarial loss, while also maintaining similar training distribution, and that's why we also have the out-to norm loss between generated samples and initial samples to enforce similar distribution. And this is the visualization of the generated data points overlapping high loss regions. And you can see that from figure A to figure B, the generator neural network gradually seeking for the high loss regions around here. Well, let's see how the proposed method performs compared to previous methods like PIN. We consider the Berger equation defined like this. We consider the viscosity of the equation to be the PDE parameter that we will vary using this form. And finally, use Bayesian optimization to search for the best alpha star under the range of from 0 to 1. The right hand side is the results section. We separate between normal training and training with noisy observations indicated by blue color. And you can see that with uncertainty quantification, our method exhibits similar performance even in the noisy circumstances. Furthermore, our method shows greater performance in terms of MAE, MSE, and relative out-to error, owing to both the multitask learning and adversarial training, which actually exhibits the best performance in this table. For the demonstration purpose, we compare training loss and MSE on the test set for each epoch, and we found that the best performing MTL strategy, which in this case is the uncertainty weighted loss function, really reduces overfitting, indicated by the dotted black box. This is the result from 10 runs of Bayesian optimization, and we found that top performing, including the global optimum alpha star, are 0.6. Actually, in our paper, we have tested the method with other PDEs as well, including the well-known high-dimensional Black-Scholes equation for financial applications here. But what's important that I want you to notice here is that the losses around nonlinearity regions are significantly lower when applying the proposed adversarial training. For the stochastic differential equation, SDE, as I mentioned, one-dimensional Black-Scholes equation, the very terms for producing an auxiliary SDE could be the drift mu or the volatility sigma, or just basically any coefficient we use to config the SDE or to config the equation. For the Black-Scholes case, I consider the volatility sigma as the PDE coefficient to vary. Remember the original value is 0.4. Then I set the auxiliary sigma to a nearby value of 0.3, and that's it. We could produce the auxiliary SDE. For those who are interested in the actual loss function for learning to solve SDE, you can read through our paper, or you can have a look at this paper as well. For the SDE case, if you look at the results, you could see that our multitask treatment is able to reduce errors in terms of MAE, MSE, and mean relative error as well. Finally, to conclude, we propose two novel techniques for learning to solve PDE using a neural network. The first method is the multitask learning for better generalized solution. The other technique is the adversarial training, which led the network to highly consider on the high loss regions. For the future work, we plan to use our method to tackle chaotic systems, parameterized PDEs, and also combine it with the traditional deep learning pipeline as well.